Okay, so for our second to last speaker of the day, we've got Theo Schlossnagle. Theo is at Circonus. He's a serial entrepreneur, and he's blessed with an abundance of opinions. So we're going to hear about some of those now. Theo?
Yes. All right. Well, I'm very honored to be almost wrapping up SREcon. It's a really fascinatingly different conference than most of the conferences I attend. It seems like there's more blood spilled and more mud here by engineers. So I find things most valuable when you share experiences of war, right? Like all of the tragedies, personal, technical tragedies in your life, when you share them eloquently, you walk away more knowledgeable. And I hear more stories that are more real here, which is fantastic. So I'm not going to talk about stories. So now I'm super uncomfortable up here because I like telling stories, but I am going to gamify this as well. I'm just thinking about everything that happened in the last talk and thinking about, like, can you cheat on your wife with a Pokemon? I don't know, does that even work? Like, how does that work? I'm pretty sure you can in the US, but maybe not in the EU. I don't know how that works. Scary. I like meat. We're getting near the end of the day. Everyone should leave here incredibly hungry. So I'm going to talk about performance, which everyone here cares about. If you don't care about performance, you should leave the room. There's probably coffee somewhere. So there's a couple of things. I want to run through how we should be thinking about performance from a terminology perspective and kind of a topology perspective. And then I'm going to talk about how, like, computers got big and fast and kind of changed the way we're able to kind of review in postmortem the performance of our systems. But I'm very soon going to get to pictures, which you have to guess about. But first, high performance daughter. Don't mess with a tiger. Just understanding what performance is. I think there's a lot of academic definitions of performance when you quantify the speed up and things like that, but when I'm talking about performance, I'm talking about the ability to deliver product, deliver it well, whether that's the actual delivery process or, of the technology, or the delivery process of the experience to the user, right? So when the user goes to your product, they leave happy. They leave as a retained customer. So that is really what port performance is. And as every SRE knows, the host bus controller on a server somewhere that you didn't think you ran because you ran serverless on someone else's container somewhere else actually can screw you completely. So you have to be aware of everything at so many levels. But that's really what it is. At the end of the day, that all rolls up to the experience of your customers and your ability to retain them and ideally either improve their lives or take their money, ideally both. So the consistent terminology for doing this stuff. So this is my Scotch bar at home, which we'll get to a much better one that I took a picture of later. But this is not the first time I've been to Ireland, and I love the country, and I love taking pictures. So almost every slide has a picture from somewhere in Ireland. There are 3 that are tricks, but if you know where they are, you should raise your hand, and I'll look out, and if you shout out and you're right, then you're not wrong. So the first thing to know about performance is that you can't improve what you can't measure, right? So the idea of being able to actually quantify in a repeatable way the performance of a system, whether or not you're measuring it correctly, is somewhat important, but measuring it consistently is paramount. So I suggest doing both, being, accurate and nice. So let's define monitoring. There was a conference 2 weeks ago called Monitorama, which is it's a great conference, very different than this one. And there was an effort made there to define monitoring that kind of went into collaborative Google Docs mode after the conference and kind of produced some interesting results, and there's a link to that up there. And what it talks about is defining what, like, components and systems and observability and things like that are. And the definition, which I'm not sure everyone's 100% happy with yet, but we're getting really close, is that monitoring is the action of observing and checking static and dynamic properties of a system. which uses a whole bunch of words that you need to define by going reading the doc. That's how definitions normally work, right? It's not like Article 29 of something, but it's something else. So, what are the static and dynamic properties we should be measuring? So when you think about performance in computing, usually you're talking about throughput and latency. So anybody know where that is? Wait, there was a picture. Anybody know? Anywhere? Oh, good, no, come on. There's so many people from Ireland here. It's on the Kerry Way. I think it's near Cair Daniel on the Kerry Way. Kerry, Ring of Kerry. Okay, great. This is a trick one. This isn't in Ireland. Okay, that's anybody? No, nobody? Edinburgh, thank you. Very good. It's during the Fringe Festival where you get to understand that throughput can be very high and latency can be very high. As you wait 3.5 hours to get into a venue with way too many people and be on fire code, but nothing ever burns in these countries because they're wet all the time. So I guess you don't have like occupancy and fire codes or something. I don't know how that works. But generally speaking, both of these things are things that you think about when you think about performance. Throughput is really a boring thing to think about. Throughput is something that typically is an easy problem to solve. There are some circumstances where it gets a little bit more interesting and complicated, but generally speaking, we as engineers are the ones that are forced to deal with latency. And we focus on latency because latency is the mind killer. It's the one thing that just screws you because you can never take it infinitely lower. You can seemingly take throughput infinitely higher, but latency, it does seem to bottom out around the physics level, right? So, now that we understand we're talking about latency, it's pretty important to talk about time. And the only thing I really have to say about time is that precision is a really important thing. Because reasoning about, like, there's a lot of systems that measure time in integers, which is okay, but you don't want to measure integer seconds, right? You don't want integral seconds of measurement. So did your web page take 0 seconds or 1 second to load? Or 2 seconds or 3 seconds? Those are really bad objectives, right? Or your disk IOP, was it 0 seconds or 1 second? Well, it's pretty much always 0 seconds, I guess. So you probably want to be measuring those things in nanos or micros. But because math is hard enough as it is, when you add units into math, it becomes one, more expressive, but even harder. So there is actually a unit of time you can always measure as long as you're not integral. So always use seconds. Just always use seconds, all right? Time is an illusion. Lunchtime doubly so. But seconds are the clearest unit of time, right? They're the only really good international measurement of time. So the number of requests you do in a day or a year might fit in a marketing dashboard or something like that, maybe, but it never belongs in a slide. It never belongs in a presentation to a technical community unless you're a cosmologist or an astrophysicist, right? You don't have to tell me how many seconds it takes to get to like Alpha Centauri. But when we're talking about technical world, you should measure it in seconds. And then we have these really handy international unit prefixes like micro and nano and femto, and they make our seconds really happy. So use seconds, don't use hours. I don't care how many requests you do per hour. So now that we know we're measuring things like latency and we're trying to, our lifelong battle to reduce latency, I think the problem that the SRE community in general really understands that the rest of the world doesn't, and this talk is about tools and techniques for having a coherent conversation, despite all of the beer. I actually have seen a lot of coherent conversations here. It's not really about how you to talk to each other. You already know how to talk to each other. It's how you and the rest of your organization can actually talk to each other more effectively, right? And the thing that you understand that they do not is that architectures, the latency doesn't really come from the components that you're thinking about. It comes from the spaces between the components you're thinking about. I mean, it's very rarely that you're actually doing something. You're usually just waiting for someone else to go do something, right? So a database, when it gets a, something off the packet, something off the network, you're actually just waiting for the packet to come off the NIC into memory, right? And then sure, you parse it, and that takes a couple nanoseconds. But then you're executing your parse tree, and you're just waiting for the disk to go do it. And the disk is actually, not doing much. It runs through like a million lines of horrible code, and then it figures out like, I want to spin around and seek somewhere, but then it's waiting for something to mechanically move. And if you're on an SSD, it's waiting for someone to wear level in the wrong way that screws you. So really it's about, as a musician, you think about like the space between the notes is really what makes beautiful music, because otherwise it sounds like a foghorn. And the architectures that we deal with are highly complex systems. They're decoupled, and there's a lot of space between them, and the vast majority of the latency happens between those connected components. And you need a way for everyone to understand those components in the same way. You have to have the same context, the same diagrams, if you will, the same mental model, the same terminology. So that's critically important. That's the
James's Gate Brewery.
Yes, James's Gate Brewery, and as is this. So understanding a performance culture, right? How do you develop that? The easiest way to develop a culture around performance is simply by celebrating it, because people like parties. Right? So when someone does a good job, you let them win, right? You celebrate these individual wins. And because some people don't seem to win all that often, they actually do, but it's a little hard to see. They're a little bit below the fold of how that works. They're always in teams, and those teams are winning, right? Through collective exercise. So when one party for one person and a good attaboy, you did a great job, here's a free dinner for you and your spouse, or you and your friend. That's sort of individual spot recognition for that stuff. And I know a lot of large companies have really intricate programs for doing peer congratulations that's actually incentive based, which is fantastic. Also make the party a little bit bigger sometimes, and actually have the team go, or 3 or 4 people could finish that, maybe, I don't know. So have larger collective wins that are actually really reported on and celebrated throughout a company to develop this culture that performance is rewarded and it's respected within the company. So that's really critical. As SREs, you're always fighting for performance, so you already know that it's important, but it's easily lost outside of the SRE group. So in developers, developers are always like, my benchmark goes twice as fast, and I'm sure everybody here is like, great, another benchmark that doesn't matter in production. But what they don't hear is when they actually made it faster in production by 1% and don't realize how big 1% is, that they're told about that. And a lot of times they just don't know. They make an improvement, or they make an improvement in the benchmark, and you go, didn't do anything. But when they don't realize they make an improvement, they need to be told. So, what does the future of observability look like, right? So now we know that we're aiming at low latency, and we're aiming at having a culture around appreciating performance in a company. What does it look like to even monitor and manage this sort of thing? And in the past, we used to go ask computers questions about how they were doing, and they would be like, I'm good, or I'm bad. I like to call that red light, green light ops. The Nagioses of the world, where it's like, hey, are we performing? Everything is green. It's like, that's not really a performance number, okay? And they go like, 3 things are orange and 2 are red, so we're doing okay. That seems really odd, right? Like, that's just not a way to talk about performance at all. So then we started taking measurements off of systems, like how you're doing, and they're like, 10 out of 10. Now I'm an 8 out of 10. I could be better, and that idea of measuring those things on systems, whether it's like request rates or response rates, error rates, things like that. You have a web server and it's doing requests. You're measuring those. So, I mean, people here have been on systems that have been performing slowly, I'm sure. And the old commands are still great commands for diagnosing system problems. So if you run things like a SAR or IOStat or VMstat or any of those things, you're getting a micro snapshot in time of what that system looks like. And then it runs an absolute frickin' eon later, which is usually around a second, which, I don't know, 2.4 billion instructions just happened. And then you get like another output and you're like, complete picture of the system. It's like, No, you don't. There's like everything happened between those 2 seconds, especially in high volume systems, especially if you're doing 1 million requests a second on a box. You got 2 snapshots of a system's health or resource utilization, and 1 million business critical things happened between those 2 measurements. So I'll tell you that you probably don't know at all what the fuck is going on your box, right? So the old methodologies were to monitor these sorts of system resource utilization aspects. And I think that applies really well when we understand how those things move. A great example of that out of the computing world is your car, right? So if you look down at the speedometer on your car and you're going 60 kilometers per hour, and then you look away and then someone jams on their lights and you slam on the brakes and now you're going 45 kilometers per hour. Those 2 mental measurements that you had, right? You took a snapshot at 60 and a snapshot at 45. The likelihood that you were going 60 and then you were going 2,200,000 and then -2 and then 45, between those, highly unlikely. Your body would be jello for one, that would be a great one. But there's an understanding of the system and its ability to change that quickly. When you're looking at things like CPU clock ticks and instructions executed, that's just not the case, right? So if I'm doing something and I'm 2% idle here, and then I go look a next second later and I'm 30% idle there, like the understanding of what happened in between those, you could have been 100% idle in between those 2 gauge measurements. So you have to think about systems really differently. So we went through this entire problem in the web industry already, right? So anybody ever run Keynote back in the day when they could tell you how your website was from like 30 or 60 locations in the world? And they did. It was awesome. I mean, I used a service. It was great. I could call my clients and tell them like, I know you're up. It's fantastic. France just loaded 3 minutes ago. They loaded your website. It came up in like 6 seconds. Fastest website in the world. This is like 1996, 1997. It was awesome. It's like 6 seconds. Oh man, I didn't even know tubes could go that fast. So you're looking at it, and then when you look back on it, I mean, that sounds like idiotic today, right? I mean, like the whole idea of doing that. It's like, okay, wait, all right. So you ran requests once every like 15 minutes from 60 locations around the world, and they all emulated people who aren't customers, right? They're like users in data, they're computers in data centers. Basically, you've just told me that you're pretty sure that if robots were my customers, that my site would work. It was good, but looking back on it, looks ridiculous. So what do we do now? The next step in that evolution was that Gomez came out with this awesome idea. It was really slick. Let's have a botnet. I mean, botnets are awesome, right? So they ran the services on users' computers. So now you actually weren't in a data center. You were on a real customer's box, but it wasn't your customer. It was like a customer down the street, unfortunately on a different telco provider than the customer that just walked away from your website because it didn't work. But it was a better idea. It got closer to this idea of like what I really wanted to measure. And what do we do now? What does everybody do now, right? You embed performance information in your site, and every time you go, you get your actual user's experience. Boom, that's really obvious. Like, does anybody here like not do that and think that's a horrible idea? Like, why would I want to know how my actual users are perceiving the site? So the really interesting part of that is that when you look at the number of web requests, nobody does very many web requests. I mean, no, I don't know. Google can probably say I can't comment on that, which would be awesome because then they can't correct me. But I don't think there's really anybody doing like 10 billion web requests a second all day long every day, right? Or 100 billion web requests a second every single day. 100 billion is a small number, right? Because I'm doing more context switches on my CPUs than that. I'm doing more IOPS than that across a whole data center. I'm doing a lot of work at very high volumes. Web rate is so slow, right? Especially the web user, because like it was a person. It was like my my 9-year-old daughter using her Nexus Android device when she's not supposed to. That was her doing that. It was caused by humans. So the interesting problem on taking this evolution of how we monitor the web into the systems world is that we're dealing with machine-induced data now. We've always been, but the volumes are much higher. And the bottom line is that I don't think, at least today, it's certainly not possible today to apply that same concept, to track all of that stuff the same way we would. So every time I do a disk I/O, I know exactly where it came from, what induced it, every single I/O and every spindle in the whole data center. Every time a process context switched, I know what nanosecond it went off the CPU. I know why it went off the CPU. I know what process followed it. Like, those are the things that you would track on a website. I want to know when they went into the shopping cart and where they came from and how long it took them and why they didn't come back to the shopping cart. What was the delay? These are all really obvious things to have, and they're useful, but I don't think it's reasonable today to track that information. So the answer is, anybody know where that is? Newgrange, that's correct. And this one actually has context. I don't know, my speaker notes aren't on here, but does anybody know where this is? No. This is in Caer-Savine, and hold on one second because I have to read my note. It's the Church of Daniel O'Connell, who was the person who ushered back in Catholicism into Ireland. Is that right, I believe? Somebody who understands how to figure out how to compromise, right? So I think it's really important to say, to not walk away and just, kind of throw your mic down and walk off the stage and be like, screw it, I can't do every transaction, I can't trace it all. So what do we do instead? And there are two simple tactics to this. The one is that we do it all, but we don't do it all the time, right? It's like Ron Burgundy, right? I am 100% right 10% of the time. So if we're able to do full system tracing through all of those things, all the way down to an IOP, but we're able to do it on 0.5% of the transactions, then it becomes really interesting, right? Now I have that super granular detail that allows me to solve problems and see things I haven't been able to see before, but I don't have that load volume and that data, that information theoretic problem that I would have otherwise. And then the second path is to lose the dimensionality of that data and actually track it. And in this way, it's like dynamic tracing would be knowing the path of every grain of sand on that beach, where it came from, how it got there, when it got there, right? It would be really cool to do that to like 15,000 of those grains of sand. It'd probably give me some really interesting insight. The other thing that would be really good to know would be to know the topology of that sand every second. Just the general topology of that sand, all the nuances, because I can do that without actually tracking the history of the grains, right? So you have these two different views. You have a very, very granular view of the world without understanding individual entities in it, and then you have a highly sampled, deep, deep view of the world, understanding individual entities in it. So what does path one look like? Path one actually looks a lot like Dapper. So the Google paper about Dapper, I'm sure Google, if they can talk about it, it's because they don't use Dapper because Dapper's stupid and they use Dapper 2. That's usually what happens. But there is a company that started up, I think it's called Lightstep, that's looking at doing this sort of thing commercially. And someone at Twitter, I'm going to skip a little bit faster. Someone at Twitter started a project called Zipkin. So basically the way this works is that you have to do a lot of work. You have to instrument your systems, and your systems start to talk to you and register, I'm about to do this bit of work. It's this offset in time. I finished doing this bit of work in this offset in time. And the idea is that you have this concept of a trace ID. So when a piece of work comes in, a user comes into the website and they start to load a request, you're like, oh, this isn't traced yet. I'm going to establish a trace ID. And I'm not sure in Dapper, but in Zipkin it's a 64-bit integer, signed, because Java sucks. Why signed? Unsigned, please. So it's half of a 64-bit int that you get. So you assign that trace ID and then you start tracking that. And as you do subqueries, you communicate that parent trace ID into the subsystems. And they say, oh, I have a parent and I have this new trace ID for my new span. And if anybody's ever seen a waterfall diagram in a web browser where you see all of the different asset loads and which asset load costs the other asset load, you get that throughout the entire distributed system. So you get service 1 calling service 2. And the beauty of this system is that in the original system here, right, you have service 1, and if you're writing your web page or you're writing your Go API server, and you understand your latency already. you're having a conversation with your team about the red bar on top. And the database team that you asked for a specific information from, they already understand service 2. They understand the green team. The problem is the interesting conversations about performance are both of those together and the space between. And the reason that NetOps in general gets their finger pointed at to them and like, chili powder poured in their eyes and whatever, is because they don't see the other two and they're always blamed for all the space in between. But with the idea of having something like a tracing system like Zipkin, you actually start to see a more comprehensive view of handoff and latency between services. There's a way to reason about the space between the products. So now you have an actual conversation to have, right? So this picture is a consistent picture in time. That's a waterfall diagram that has different components owned by different cross-functional teams, right? So now you have what you really want, which is a good conversation. The reason this doesn't work well all the time, does anybody know where this is? Tato Park! We have a lot of theme parks in the US, but this was actually pretty fun. This was good. So the problem is that when you start looking at this idea of doing these sort of traces, and you take this to the nth degree and you start talking about every disk access, every sector seek, all of those things, this thing explodes. It gets enormous. It's not useless. It's incredibly valuable. It's just super incredibly expensive, right? So the return on investment of doing this all the time, it never makes sense. So Zipkin, real quick. There's an Open Zipkin project now. You can go to Open Zipkin. Pretty interesting software. I think that they are currently struggling with the implementation of their governance model, to put it politically correct. So that's sort of interesting. It's built on Scribe. Scribe is a tire fire. It's terrible. I don't think Facebook uses it anymore. If they do, they probably use it for only non-critical things. So Thrift is an encoding protocol, and Scribe is an RPC protocol. And Thrift is a set of burning tires, and Scribe is a large pile upon pile of already burning tires. So the idea is that I'm going to put this trace into the system, which again, it's using Thrift, so you can't represent unsigned types. Okay, so, and then I'm going to encode it in a Thrift string. But Scribe takes strings as its arguments, like by default, the Scribe implementation of Zipkin. But I have this Thrift encoded thing, so how do I get some binary blob into a string? Anybody? Base 64 encode it. So you base 64 encode this thing, but then it has to be rethrift into the Scribe protocol. So I had a yo dog, I heard you like thrift, so I put thrift in your thrift, but there weren't actually enough thrifts in that picture. So that doesn't make any sense. Did I just crash? No. Okay. So screw Scribe. Does anybody know where that is? Anybody know where this is? Trim Castle and the stumbling stairs, which were a brilliant, horrible idea. Right, all the stairs are uneven going up, so the invading army trips as they go up the stairs, and then you cut their heads off. They're very graphic when they describe it. Really clever, but you're not supposed to do that when you're building software for someone else. Pro tip. So what we did is we kept Thrift because the two ends of the system need it. But what we did is we jammed it on FQ, which has lockless publishing. It's asynchronous. It's kind of like a diskless logging infrastructure. It can be used as that. And then we consolidated all of Zipkin's bad Scribe decisions in a little tiny binary that pulls off of FQ and publishes into Zipkin. So always isolate the hell in the smallest possible ring. And then they only had Java and Scala support, so we wrote, where is this? Everywhere happy. Okay, that's the answer. We wrote C support and Perl support that are both open source for that. And what ends up happening is you get traces that sort of look like this. You get service level traces. I can see the URL of something that's coming in. I can see like the different operations that are happening. And if the other end of it is instrumented, then you can also see the second level service pick it up. So if Postgres itself was, for example, had Zipkin support, you could see it start to plan its queries and hit its files. You could see it read off of its files and things like that. It's pretty fantastic. So day one, we found a bug in the code that shaved 350 milliseconds off of every graph we drew. Fantastic. So we run a monitoring system. So it was affected every single user. And then within a week, we also shaved off about 150 milliseconds off of a large set of other calls due to asynchronous DNS timing issues in libcurl, which were fascinating to just to see something spelled out and you're like, 150 milliseconds isn't a lot, but it's not always there. Why isn't it always there? Just all the right questions start coming out. So really, that's the answer for distributed tracing is you need a tool like that. And I think right now there's some competing standards out there, but Zipkin seems like the one that's most easily digested by teams. Like if you're gonna just try it out, you can spin it up in probably an hour and get it working. So for the other side, so this is how you track the 15,000 grains of stand. Now, how do you get a snapshot of a granular view of the beach to understand what it looks like? And there's a reason that you want to do this. And the reason for this is that when you're tracking high volume data, you can make strong statistical assertions about that data more quickly. If I take data every minute, and then after, say, 15 minutes, I have a model, how many new data points do I have to take before I am confident that my statistical model is being violated? The number of data points is fairly consistent, but if I'm taking that every minute, that number of minutes is very large. But if I take 100 samples a second, for example, I have a much stronger and more consistent model of my system, especially if I'm observing those things. I'm not actually synthetically testing them, I'm just receiving that data. How long did every IOP take? How many people have watched average search service latency times on their disks, right? With IOStat, you can see it. It's like average service latency is 9 milliseconds. You know how many disk IOPS happen on a system in a whole second? Like 9 millisecond average is not a useful piece of information at all. Really what you want is a distribution of all the individual latencies of every IOP you did. So what does that look like? It looks like a histogram, right? So you store your data, and we've already had talks talk about this, but store your data in histograms. Store as many samples as you have. Like, try to do 100% sampling. All you're doing is taking a measurement and jamming it in a histogram. So you store that, and these models are a lot easier to reason about. And it's a lot easier to understand with a new high volume bit of data comes in, high frequency data comes in. You can quickly ascertain whether or not the new data coming in fits the old model. So you can start alerting on things in 500 milliseconds or 100 milliseconds as opposed to a minute or 5 minutes. What happens when you take this histogram, turn it sideways and move it over time, right? So now you have time series histograms. So you can see the distribution as you roll through. This is the exact same histogram. This is a pretty version, and then up in the little corner, this is the exact same histogram, which is what that gray line is. So as I move the mouse back and forth, I can see all of the histograms. I can see that change over time. And a lot of people think that latency is a really important thing, and I'm one of them. So all latencies should be tracked this way. But it's not only useful for latencies, it's useful for anything that you observe. So for example, how many people here run message queues of any kind, right? And they put, I guess you put messages on them, right? Yeah. How big are they? I know every benchmark is done with a 1 byte message because screw you, those are useful, right? But how big are your messages? How many people here know how big their messages are? Probably, I see one hand. That's nuts, right? That's crazy. It's a critically important piece of information to understand how big your messages are in your message queue. Because one, it directly impacts performance, but it's also illustrative of behavior changes in the underlying system, the subscribers and the publishers, namely the publishers, right? So what if instead of tracking the latencies, or in addition of tracking the latencies of every message, you track the payload size, right? And you start to see payload distributions. And I can see that, right? And this is over the course of, I don't know, is that like a day? That's something like a day. So that's a day. That's 240 million data points. There's 240 million messages sent in that day period, right? So that looks really, really monotonous. If I zoom out to 7 weeks on that, that's 45 billion data points that are being illustrated there. And it's really clear that I have at least 4 distinct behavioral patterns there, right? You can see there's basically 3 changes. There's before the first one and then the next 3. It's really, really interesting information, right? So you can detect the changes in the behavior of a system. The average in this case didn't really change very much. things shifted around. Some got littler and some got bigger, but understanding the behavior of a system, this, in my perspective, is what is going to start happening to every component of a system. And the technology needs to change slightly because this is 2 data points. There are 2 streams of data, right? So this is message size coming into one message queue and it's backup. That's all it is. And it's 45 billion points of data, right? And now if you look at your architecture and think, I have 10,000 servers, I've got 1,000 different microservices running, I want to track latencies on them, I want to track request response size, I want to track different functional activity on them. You're talking about 100 trillion data points easily over the course of a day, right? So we need to change the way we think about this, which is why histograms are so important. And obviously you don't want to have that graph take like 6 minutes to load, right? So you need to be able to make operational decisions on it. So those are the 2 big challenges that I see in the way that we do monitoring. The idea of red light, green light is gone. Now we're all looking at graphs that are coming in slowly. The way it's going to change is we're going to start looking at traces that are incredibly descriptive traces, and we're going to start looking at behavioral pictures of data. And those are the 2 trends we're going to see going forward. And that's what I wish my Scotch bar looks like. And that is a mere 10-minute walk to St. Stephen's Green. So, that's it.
Do we have any questions for Theo?
Have you put any thought into how to visualize this kind of rich data for people that are visually impaired? Because I kind of worry that as we get more and more towards doing this, we're not going to be able to have people who have disabilities working in SRE, and that really concerns me.
The answer is I have a lot of thoughts, and I'm not convinced that any of them are really that high quality yet. So I think that I haven't met anyone yet who doesn't understand a straight up histogram. But once you put that into 3 dimensions and you have time series histograms, and as soon as you actually use a 3-dimensional model, everybody colors it. Now it's 4 dimensions. There is a huge traction problem on understanding, and we haven't conquered that yet. But I think that visual aids and hints, so that the kind of the 2-dimensional, if you're looking at a kind of a 3-dimensional representation, the constant surfacing of the 2-dimensional slice you happen to be looking at right now my hope is that can reinforce the mental model for the first one. But I'm not convinced that that's right. I think a UX expert really needs to get on this.
Okay, thank you.
Okay, let's thank Theo again.